Okay, so for the following circuit, we have to find a VR, and then after we find VR, we have to find VRT. So sorry, we have to find V and then VRT. Okay, so we have to first find this, and then after that, we have to find this. So let's start by viewing the circuit when t was less than 0. So when t was less than 0, our switch was, so this portion of the circuit doesn't exist. It's only just this part we're focusing on. So we'll rewrite the circuit as the following. Okay, so this is 1 ohm, this is 2 ohms, and this is 12 volts. Now we're going to assume that the circuit looked like this for a very long time. So obviously this portion, the capacitor, becomes an open wire. And now we have to find the voltage at this region. So first let's find the current. The current will be passing through around here. So it will be 12 over 2 plus 1, which will give you 4 amps. So the voltage here will be the same as the voltage here. So it'll be 12 minus 1 times 4, which will give you 8 volts. So that means when t was less than 0, the voltage at this capacitor was 8 volts. And the second t is equal to 0, obviously the voltage at a capacitor can change instantaneously. So that means this will still be 8 volts. So we'll write V at 0 is equal to 8 volts. Now let's view the circuit when t is greater than or equal to 0. So when t is 0, we flip the switch and to point B. So our circuit now looks like the following. So this is minus VR. This is 2.5 henries. This is 1 over 40 farads. And this is 10 volts. So the first thing we're going to do is write a transient circuit. So pretty much what that looks like is we just pretty much ignore the source, okay? So we're just going to ignore this for now. We'll deal with that later on. So this is going to give us the transient voltage at this capacitor. Okay, and then after we get that, we need to find the steady state voltage at the capacitor. Then we just add those up and we'll get our final voltage at the capacitor. Okay, so first let's find this one. So this one we're going to be using this circuit. We'll do a quick mesh. So we'll just do the following. So it'll be VR plus wait, sorry, so not VR. So this is obviously we're gonna say this is I. So it's gonna be 10I plus the inductance times the change in current over the change in time. That'll give you the voltage here. Plus plus the voltage at this capacitor. Okay, we're gonna do that, and then we know the following is true. We know I is equal to C times dV over dt. Okay, so what we're gonna do is plug in I for these two. Okay, so it'll be 10 times C dV over dt plus L, the derivative of this, which will just be C d squared V over dt squared plus V. If you're wondering why I didn't just find the formula for current passing through a capacitor, which will be like 1 over L times the integral of V dt plus initial I, and why I just plugged this into here is because we're trying to find the voltage at the capacitor. If we were to just solve this out, this will give you the current passing through the inductor. So that's why I need everything to be in terms of V. Okay, so now what I'm going to do is set S to be equal to dV over dt. So it will be LC S squared plus 10C S plus V. Sorry, it's just, sorry, plus 1. Now divide everything by LC. So it'll be S squared plus 10 over L. Obviously the C's will cancel out for this one. Times S plus 1 over LC. Okay? Now I'm going to do the, we could do the quadratic formula, but we do know that alpha will be 10 over 2L. So pretty much it's just alpha is going to be this value times 1 over 2. And omega is just going to be the square root of this value. So it'll be 1 over square root of LC. Okay? Now let's find alpha, which will be 10 over 2 times 2.5, which should give you 2 radians per second. And omega, it's 1 over the square root of 2 times 5. Sorry, well, hold on. 2.5, my bad, times 1 over 40. And that will give you 4 radians per second. Now we see omega alpha is less than omega, so that means it's under damping. And to find the voltage passing through the capacitor, we're going to be using the following formula. Okay, so we're going to use the following formula. We need to find WD. So to find WD, we're going to use this formula. Okay, so this is minus 2 plus minus 2 squared minus 4 squared. And that should give you the square root of 12j. This is your alpha. 2 is your alpha. And your WD, which is your damping frequency, will be the square root of 12. So whatever is being timed by your imaginary value. So this is going to be e to the power of minus 2t times a1 cos square root of 12t plus a2 sine square root of 12t. Okay, now all we have to do now is find a1 and a2, and obviously this is equal to vt. So we recall, we know what sorry, I forgot one more thing. This is your V transient voltage. Sorry, not your VT. Your okay. So if you recall, so we just solved for this part. We now have to solve for this part. Then add to this to get your VT value, and then we can solve for A1 and A2. So to find, so VSST is pretty much going to be equal to the voltage of the capacitor when t goes to infinity. Okay, so let's redraw the circuit. This time we're going to include our source. So this is 1 over 40 farads. This is 2.5 henries. This is 10 ohms. Okay, so as t goes to infinity, this short circuits and this becomes an open wire. So we have to find the voltage here, and that'll be our voltage to infinity. So obviously, since there's no current passing through here, this is going to be useless. And since this was 10 volts, this is just going to be 10. So now what we have to do is just add 10 to this, and that's going to be your V2 value. Okay, so it looks good. Now we can solve for A1 and A2. Okay, so for A1, so we know that when t was equal to 0, our voltage was equal to 8. So we can do the following. Wait, so this is just 1 plus 0 plus 10. So this will just be minus 2. And that's what your A1 is going to be equal to. Wait, sorry. Yeah. Your A1, that's what your A1 is going to be equal to. So now we have to solve for A2. So what we're going to do is we're going to differentiate all of this. Okay, and obviously this, wait, sorry. So wait, we're going to finding the derivative of all of this. Obviously the 10 goes away because that's a constant. And we just continue what we were originally doing. Alright, so yep, that looks good. Oh yeah, and then we know what A1 was. This one was just minus 2. So this and this, the negatives cancel out, so we just have the following. Okay, so that looks good. Now we just have to find dVt or over dt at a specific point. Okay, so so to find dv over dt, we're going to use the following formula here. I over c equals dv over dt. So we have to find I when t was equal to 0. So to figure this out, it's going to be a little like tricky to comprehend this, but like let's view the circuit here. So we need to find what the current was the second the switch was moved to here. Okay, so when the switch was at this region, current passing through the inductor was 0. Okay, because this is detached from the rest of the circuit over here. But the second we flip the switch to this region, obviously the current passing through the inductor can change instantaneously. So that means the current passing through the inductor is still 0, and that means the current passing through the capacitor is also 0. So that means this is just equal to 0. So dv at 0 over dt is equal to 0. So that's what we're going to plug into here. This is going to be 0 minus 2 a1 plus, sorry, hold on, sorry, a1 plus 0. Oh yeah, and recall a1 was minus 2 plus 1 times, okay, this is all 0, plus the square root of 12a2. Now this will just be 4 plus the square root of 12a2. So it'll be minus 4 over the square root of 12, and this is a2. Okay, so that's done. So now we can solve for Vt. So Vt is equal to e to the power of minus 2t times minus 2 cos square root of 12t minus 4 over square root of 12 sine square root of 12t, and then plus 10 at the end. Okay, so now we have to find Vr of t, and so we see for Vr, which is this, Vr is going to be equal to the resistance times the current passing through it, and I is going to be equal to so the I passing through here is the same thing as the I passing through the capacitor. So I is equal to the capacitance and the change in of voltage over the change in time. So I'll just plug that into here. Okay, and now that's going to be how you find your VR. It's equal to 10 times the capacitance, which was 1 over 40, times the derivative of all of this. So let's start. So it's going to be minus 2 e minus 2t times times minus 2 cos square root of 12t minus 4 all over square root of 12 times sine square root of 12t. Okay, and then obviously this just goes away. Plus e minus 2t times minus 2 square root of 12 times minus sine. So obviously this goes away. Square root of 12t minus 4 over square root of 12 times square root of 12 times cos square root of 12t. Okay, that's that looks good so far. Okay, now what? So let's FOIL everything in. So this goes into here, so it'll be 2 e minus 2. So it'll be 4 e cos square root of 12t plus 8 all over square root of 12 sine square root of 12t plus e minus 2t times 2 square root of 12 sine square root of 12t minus 4e minus 2t, because obviously this and this cancels out, cos square root of 12t. And notice this and this should cancel each other out, so this and this are gone, and all of then we'll just add these two up, times by 140 times 10, and let me see what that gives me. You should get the following: 2.309 e minus 2t times sine square root of 12t, and that's your VR of t.